All right, let's talk about heating and cooling curves and also how to calculate how much energy is required or released during a phase change. So first it says below are a generic heating curve and cooling curve for any substance. Please write down at least 3 observations about each that you notice. So let's look at the first one. So I see, I'm going to get a highlighter here. I see that it's starting out cold and it's heating up to this point where it's melting and then it's staying flat. So the energy is being added and yet the temperature is not rising. And then the temperature does rise again after melting, and then it plateaus again when the substance boils, and then it increases again. So this whole time heat is being absorbed over time. Okay, so one big observation is during the phase changes, temperature does not rise, right? During our melting and our boiling, it does not rise. Another thing that I'm noticing is I'm seeing that during all the parts where the temperature changes, so I'm going to just make these blue now, that it says that the kinetic energy is increasing while the potential energy is staying the same. So during temperature increases, the kinetic energy is increasing, but potential energy stays the same. And then it's the opposite during the phase changes. So when temperature is plateaued, the kinetic energy stays the same while potential energy increases. Okay, and let's look at our cooling curve. So in our cooling curve, we're starting up and high, it's a gas, and then it's cooling and it's going through condensation and it flattens out, and then it cools down again. It flattens out during freezing, and then it cools down again. So once again, during the phase changes, in this case condensation and freezing, the temperature stays the same. It doesn't continue to go down. And then similar observations as last time, during condensation and freezing, the kinetic energy stays the same while the potential energy goes down. During temperature drops, so during the slants, during temperature drops, kinetic energy is going down and potential energy is the same, staying constant. Okay, so let's learn a little bit more now that we've kind of made some observations. So some important definitions here. Freezing point is also known as fusion, and melting point. These are the temperature where a solid is going to a liquid or a liquid is going to a solid. And of course, we know that melting is going from a solid to a liquid, while freezing is going from a liquid to a solid. So just to make that clear. So water freezes at 0 degrees And ice melts at 0 degrees. It's the same. Okay, boiling point is also known as vaporization. That's going from a liquid to a gas, while condensation is going from a gas to a liquid. And similarly to how the freezing point is the same as the melting point, water boils at 100 degrees and gas also condenses to go back to being a liquid at 100 degrees. Let's check out a heating curve and label some things. So this is for water. So we're starting really, really cold. Like, let's make something up. We're starting at maybe negative 20 degrees Celsius. So this would be ice. Okay, so a solid increasing in temperature would be right here, this yellow part. The melting point would be here. So ice is finally melting. And then a liquid increasing in temperature would be here. This is where it's a liquid. And then vaporization point, where it's undergoing a phase change from a liquid to a gas, is here. That's where it's boiling. And then we need another color for, oh, here's a light pink. A gas increasing in temperature would be here. Okay, and then it says label a time where there's both liquid and gas present. So that would be here during boiling, right in the middle. There's both liquid and gas here. Okay, so I'm going to label solid. This is solid and liquid. And then we've got liquid, liquid and gas, and then we've got gas. And again, boiling is happening at 100 degrees, so that's why I matched up the plateau with the 100, or that's why it is, and then it melts at 0. Okay, so what about the opposite? What if we're starting with steam, maybe at 120 degrees, let's say, and we're cooling this down back to be at negative 20, ice, let's say. Okay, so we need a gas cooling would be here. Condensation point, where it's changing from a gas to a liquid, would be here. Liquid cooling would be here. A freezing point would be here. And a solid cooling would be here. A time where both solid and liquid phases are present would be here. This is liquid and it's turning into a solid. This is solid. This is liquid. This is gas and liquid. And this is gas. Okay. So let's get into this energy stuff. It says kinetic energy changes as the temperature changes. So if something has a lower temperature, the molecules are moving slower. If something has a higher temperature, the molecules are moving faster. Potential energy is all about the distance between molecules. So if molecules have a lot of potential energy, then they're going to be spaced further apart. Then when they're having a low potential energy, they'll be close together. So during melting, as the potential energy increases, the molecules spread out from how they were as a solid to further apart as a liquid. Okay, so let's make sense of this with the cooling curve first. So kinetic energy is going down as you go down this slope, and then boom, it's condensing into a liquid. So the particles are moving at the same speed, but they're moving closer together. Then the molecules slow down again in their liquid form until they hit their freezing point, where it stays the same temperature, but they're moving closer together. And then they're as close together as they're going to get, and it cools down further as the particles slow down. Okay, heating curve is the opposite. So, okay, you've got some ice maybe, molecules start speeding up, and then they melt. Temperature stays the same. The added energy is going to moving the molecules further apart, increasing their potential energy. Then the molecules stay their same distance apart as they move faster and faster. And then they hit this boiling point where they move at the same speed, but they're moving even further apart as potential energy goes up. And then they're as far apart as they're getting, and then they speed up even more as a gas. So why does the temperature rise, fall, or level off? Well, when there's a change in temperature, that's when the kinetic energy is changing. So the molecules are speeding up or slowing down. When there's no temperature change, the plateaus, the kinetic energy is staying the same since there's no temperature change, but the substance is still gaining or releasing heat energy. Okay, because that has to happen in order for the potential energy to be gained or released, for the molecules to get further apart or closer together. Okay, so in class, we did a little experiment where I attached a temperature probe to my laptop and started measuring the temperature over time. And I started at like 85 degrees. It went up to like 90. It was going up fast, 96. And then basically it just stayed at 99.2. And I had a lot of water, so it would have been way too long to wait for it all to turn into steam. But the temperature doesn't continue to go up once it reaches its boiling point, because now added energy is being used to break intermolecular forces, intermolecular forces between water molecules to change their phase from liquid to gas, aka add potential energy to increase distance between particles. Okay, we've actually learned how to calculate the energy during a phase change, or I'm sorry, during a temperature change, right? We learned about Q equals M times C times delta T. But if the change in energy was zero, like during a phase change, this equation wouldn't work, because that's not true, that the energy required to change a phase is nothing. Okay, it does take energy. So we need a new formula. And with that formula, we're going to need new constants. So there's the heat of fusion and the heat of vaporization. Okay, for energy required or released from melting or freezing, so you're going from a solid to a liquid or a liquid to a solid, you use the equation delta HF, so the heat of fusion for the substance, times how many moles of it. So for example, you might have some value like, okay, I'm making this up, it takes 100 joules to melt 1 mole of this substance. Okay, and you're trying to melt 2 moles. So the energy required would be 200 joules. Okay. All right, and very similarly, if you're trying to calculate the energy required or released for vaporization or condensation, you would use Q vaporization equals delta HV times moles. All right, so let's look at a couple example problems. How much energy is required to melt 3.00 moles of ice at 0 degrees Celsius? Well, what equation are we going to need to use? The one for melting was QF equals delta HF times moles. Okay, again, I just got that from right here. Energy required for melting is right here. Okay, now we have to look up the value for water. So on this little chart right here, to use for melting and freezing for water is 6,010. 6,010 joules are required to melt each mole of ice. So we're going to take 6,010 joules per mole. And this problem says we're trying to melt 3 moles of ice. So I'm going to get out my calculator and type this in. 6,010 times 3, 18,030 joules. Another question, how much energy needs to be released in order for 4.5 moles of 78.3 degrees Celsius ethanol to go from gaseous ethanol to liquid ethanol? Okay, so this time we're dealing with a different substance, and we're also dealing with liquid, or yeah, gas to liquid. So we're going to need this number. So our equation is Q vaporization equals delta H vap times moles. Okay, and that number again was 38,600. That's how many joules it takes to condense 1 mole, and we're trying to condense 4.5 moles of ethanol. So 38,600 divided by, divided 38,600 times 4.5, 173,700 joules. That's how much energy it takes to, needs to be released during that condensation. You can use a negative, or you can use the word released. All right, last one. How much energy is required to boil 28.9 grams of 100 degrees Celsius liquid water? Okay, well, we're going to need this formula for boiling like we just used. But crap, we don't have moles. We have grams of water. So we need to review how to get this into moles. So first thing, we need to look up the molar masses for these. Like H is 1.008 grams per mole from the periodic table, and oxygen is 16 grams per mole. So if I add that up together, 1.008 times 2 plus 16, that's a molar mass of 18.016 grams of H2O in every 1 mole of H2O. So 28.9 divided by 18.016, answer 1.6 moles of H2O. That's how much we're trying to boil, 1.6 moles. Okay, so we need the value, the heat of vaporization value for water now. 40,700. That's how much energy it takes to boil 1 mole of water molecules. And we're boiling 1.6 moles. So 1.6 times 40,700. Answer, 65,120 joules of energy. So really it's just a matter of using the table to figure out what needs to be plugged in where, and sometimes you have to do a little extra conversion to get your number into moles first. So that's it. Hopefully that helps.